Next we'll look at setups for hands. In Character Kit 1, we covered the basic setup process for hands. You can use one joint if you want for the palm of the hand, or you can use 4 individual joints going up to each of the fingers. For the fingers themselves, obviously you'd use 4 3-jointed chains, setting the pivot points exactly where the knuckles are of the fingers. The thumb is done similarly, with the last joint coming out like this. Once it's enveloped together, we can get a pretty good range of motion using this setup. This will allow us to deform the hand properly, and in most cases we'll be able to get lots of realistic poses out of this setup. For some motions, inverse kinematics, like I'm using right now, will work okay, but in most cases you'll want individual joint for joint rotation control to get the poses and the movements that you need. Of course, in Softimage there's no X-ray mode for skeletons. They don't show through, and so sometimes they're hard to select. One way around this is to turn on Show Controls. Depending on how big your model is, you'll probably be able to see these circles which appear on the chain as soon as it's enveloped. The circles show the deformation area of the joint, but in addition you can use them to help grab each individual joint for rotation purposes. Since they stick out of the flesh of the hand, they're handy that way. Now the reason inverse kinematics isn't always useful is because you can't control very well how the inverse kinematics solves the position of each of the knuckles. So it can be very difficult to strike certain poses. For instance, if you wanted the last joint to bend backwards slightly, you wouldn't be able to do it with inverse kinematics. So the forward kinematics is more useful. You'd mostly want to use inverse kinematics when you want the fingers of the character to stick to something, and I'll show that in a minute. Using just the default skinning parameters, the joint areas won't look very good because the skin underneath will collapse as the joints rotate. So you can see that doesn't look very good. The skin actually loses volume. To some extent we can fix that by grabbing the joint and going into Skin Deformation Parameters, Inner Side, like we did with the bicep, only this time we'll choose the finger option. When we come out of that, we can see that the finger instead will bulge out, but that's too much. We'll click on it again, drag it down just a little bit. That looks a little bit better. So now when I rotate this joint, the finger won't collapse quite as bad. We can do the same thing on the first joint. Choose finger. You can see how that bulges out. If you find that it bulges too far, like this one, we can go in and change the start distance like before. Let's try that now. And that's great. Now it's only bulging in this area instead of all the way down here. We can do this for each one of the fingers. It'll give us a better result. Unfortunately, we have to do this one by one, since we can't grab them all together and do it in multi-mode. Having this sort of relaxed pose to each of the fingers helps the envelope look better when it's animated. It'll look better than if the fingers were stretched out like that. If you have to model things in a very straight position before enveloping, then when they go to crunch together they don't look quite as realistic as when you already modeled them that way in a relaxed pose. There are lots of ways to animate the hands once you have it deforming correctly. Again, the most direct way is just to grab each joint and rotate it. Once you have it in position, you can save a keyframe. But keep in mind that you can also keyframe the whole hand together, multi-selecting all the joints. So if I deselect that, I can come in and select all the joints and set a keyframe all at once for all the joints together. This way we can sort of build a library of poses. For instance, if we go to this pose right here in the dope sheet, you may find it faster to get around in the dope sheet just by dragging with the right mouse button, since it doesn't update. When you get there, you can hit the R to refresh that frame. Here's a pose I built earlier. If I want to drop this on another frame, of course all I need to do is right drag to another frame and then hit Save key, and then I'll get saved again. So now as I drag the timeline, it'll go to that pose that we saved a second ago to the new pose. So again, we could build a library of poses and then just by right dragging in the interface drop them onto a new frame. Another benefit of this method is we can choose any in-between frame where we like the shape. For instance, this frame is in between these keyframes for all the fingers, but all I need to do is right drag to a different frame and hit the Save key with all of them selected, and we get a brand new keyframed hand position that looks like that in-between one. We can speed things up a bit if we go into Setup and change the surface precision to 1. We'll get better response time. We'll go back to single mode. If you ever accidentally save over the default pose that you may have put on frame 1, like this, I'll just save a keyframe. Now instead of our default pose, we have this new pose on the first frame. If you want to get that back, again it's very simple. You'd select the hierarchy and go into Reset Actor. And then before you do a refresh, you would select that joint again and save a keyframe over it. Now when I hit refresh, it'll stay in the default position. By the way, those points that jumped out, those are due to the Quick Blend plugin moving the edge points of the finger. After a few operations like Reset Actor, it takes a refresh to get the points to stick back on right. There's a couple ways you can make it easier to select all the fingers. We can grab them all in the schematic view and then do Select, Set Name Selection. Then we can give it a name. We can call them Fingers Left. Then anytime we want to access all those, we can grab on the icon itself and double click on that. Or we could simply hit Enter to go into Info Elements and go into End Selections. Click on this and then do Select Node once, twice. Then all of them get selected. We can quickly go into Save Key and save a rotation keyframe. Another way to make it easier is to make all the other things around it to be unselectable. This is a fairly new feature in Softimage. You simply grab all the geometry, all the end effectors, all the roots. I'll just hide those quick to make sure that's all we need. And then go into Select, Selectability, Toggle Selection. In the dope sheet they get a little box around them like this, showing that they're not selectable. Of course they're selectable in the schematic view, just not in the regular interface, the other views. Now if I multi-select this whole region, see we only get the joints selected. So that's a very quick way to select all the joints. Also remember that you don't have to rotate each joint in turn, you can rotate them all at once. So I can select them all, rotate on Z, and they'll all move at the same time. This way you can achieve poses that you just couldn't do with inverse kinematics, again because the chains rotate both front and backwards. I'll just right drag to a new frame and set a keyframe on all of those. Of course you won't want the fingers of the hand to have the exact same timing, so after you've done one, you can always reselect the joints of one finger and change their timings in the dope sheet to be offset from the other fingers. Rather than each joint though, keep in mind that you can also go to single mode and select that hierarchy as a whole, and then manipulate its timing in the dope sheet as a whole. So this is now the rotation of the whole chain, each of these joints included. Since all the keyframes were on the exact same key, we can now move those around very quickly. So if we wanted the index finger to lag a bit behind the other fingers curling, we can simply grab that region in the dope sheet. Using Shift middle mouse button, we can push those keys up a bit. That looks a bit more natural. Of course, all these operations are undoable and redoable. We can use this method to generate a library of hand poses to just drop in various keyframes too. If we just select the root of the whole hand chain, then we can see all its keys in the dope sheet. These are all the keys for all the fingers throughout the whole animation. On the ones where we set a keyframe for every finger, that can be considered a whole pose. We can always select that pose in the dope sheet and do a copy and then a paste operation somewhere else. And again, we can drag that around to whatever frame we want. Remember that in the dope sheet, if we have any of the timelines selected, only that part will update. So the skin isn't updating and nothing else is updating, only the part we have selected, which is the whole hand hierarchy. If I have only one of the fingers selected, or the thumb, and I have a selection region, again, only that will animate. If I right click in the dope sheet, I can get that to disappear and the whole scene will update. So that was similar to the method shown before when I had all the fingers selected, only this time it's a little bit easier because we only have the one hand channel to deal with. We can copy paste from there. The only thing we can't do with this way is select an in-between pose and copy that and paste it somewhere else, like we could with the method where all the fingers were multi-selected. Another way of controlling the fingers of the hand would be to get a new null. You can simply link the rotation of each of these finger joints to this null using an expression. So we would want to link its Z rotation to the new null, its Z rotation. then by rotating in Z, we can get that working. But then also we can go in for each of the other joints and do the same thing. We'll just do copy to copy that same expression on to the other two joints. Now it's a simple matter, just by rotating this one null, we can get the finger to take any number of poses. We can also link the Y rotation of just this bottom joint for additional control. We'll go into the Y rotation, link that to the null's Y rotation. And that way we can open and close the fingers on the Y rotation in addition to the whole finger's Z rotation. This setup can get a lot of poses, but it can't get every pose that the finger would want to take. For instance, if I just delete the null, that'll get rid of the expressions. Of course, what it can't do is something like this, where the top is rotated a lot more than the first joint, like that. So to have really the ultimate level of control, you need to add more null controls, and then it's just not a whole lot more useful than just grabbing these joints and rotating them as it is. When you're enveloping a NURBS hand, it's much easier since you can, of course, go in and select each one of the fingers as a separate object. And then also, when you're doing the weighting, you can go into tag, points, row, and U, and then grab these rows very quickly for weighting. With a polygon hand, that's harder to do. Since they're all joined together as a single object, it's harder to grab one single finger and work on it. Plus, you don't have the ability to select a row of points in U. One thing you can do, though, is use proportional modeling to pull the fingers apart. First, we would need to save a shape keyframe on this hand the way it is. So we go into Save Key Object Shape. Now we can deform the fingers and pull them apart. And when we're done, we'll make a cluster out of those tagged points for each of the fingers, so we can access them really quickly. First, I'll go into Edit Proportional Setup. I'll turn on Consider Neighborhood, and then we may need to change this distance limit here. Again, the Consider Neighborhood means that it won't look to the adjacent fingers as long as the distance down the finger and up the other finger is less than 1 that we said in that dialog box. So I can safely move that away like that, and it won't affect the other finger. I can pull there, I can pull there. If I pull too close, then it will grab the other finger because the distance between here and up the other finger is less than 1. I can keep pulling these apart. Remember that we've saved a shape animation, so we don't have to worry about the state of the finger. But now with those apart, we can go in and tag all those points without worrying about taking the points of the other finger. And again, we could do the same thing to move the other ones out of the way while we work on that. Once we have the part selected that we want, we can simply go into Tag, Set Cluster, and give it a name, Index Finger. Now I can just hit refresh to get the hand to pop back into position. We have the tag points of the index finger all selected now, so we can more easily do weighting. Now it'll be a matter of unselecting parts to get the points we want for weighting. We can always go back in the cluster list and select that group of tagged points to access it quickly. This method also works great for modeling the eyelids and the mouth, since if you dial this number low enough, then you can drag the upper lip without it affecting the lower lip. Since a keyframe target of a finger like this won't automatically move in an arc, if you use inverse kinematics on the fingers of a hand, you'll need to make sure the IK target moves in an arc motion, so the fingers don't open in an unnatural straight line in between an open and closed position. Also remember that you can use inverse kinematics to get the finger into position, and then once it's there, select the joints and then key them using forward kinematics. And of course there are times when using inverse kinematics is very beneficial. For instance, if your fingers or hand are coming in contact with another object. Like in this case, his hand comes down and then makes contact with these nulls set in position on this concrete wall there. As I move the hand around, the fingers will stick where they're supposed to be. That way, rekeying any of the arm position or the shoulder position, the body position, won't require me to rekey each of the fingers separately. You can attach them by using position constraints, of course, but in this case I already had the end effector's position constraint to these control objects here for positioning each one of the fingers. So the end effector was attached to a null, and then the null was attached temporarily to these nulls that were stationed right here on the concrete surface. First you would use the position constraint, and then you would simply deactivate those in the dope sheet by dragging a region and then hit activate or deactivate. And make sure you do that not on the translation track, but on the constrained position track right here. So let's reactivate that, move that down there. Then you can see how you can activate and deactivate the position constraint. If I go ahead and multi-select each one of those that were position constrained, and then expand each one of those tracks, you can see how each one of the position constraint tracks has the same deactive and active portions. And that was simply done by dragging that down and then changing that from an active state to a deactive state. The only problem with this method is that if you ever need to change the frame at which that deactivates, that's quite a bit of work, and you have to go in to each one of these channels and add an extra frame of deactivation, for instance. It worked great in this case because it makes contact with the surface and then stays there and comes off. Since I never changed that, it was just as easy to use this activation and deactivation process for each of the fingers. The one thing you do have to be aware of, though, is to set a keyframe right after or right before the deactivation or activation takes place, so that you don't get a pop in the position of the fingers. For instance, if I go back a frame where it's deactivated and I move these out of the way and then save a keyframe, on the very next frame they'll pop to their constrained position. In Softimage there's no smooth blending of constraints. It's either a constraint on or a constraint off. So you have to manually fine-tune that constraint change to make sure that there's not a pop like that. And again, an easy way to do that, now that we've screwed up this one frame previous, an easy way to do that is to go to the frame when the constraints are active and then right drag to the last frame and lay explicit translation keyframes down, do a refresh, and then we get a smooth transition. Just a matter of taking the position constraint location and then setting a keyframe right before the position constraint actually goes into effect. Of course, when you do the same thing after the position constraint becomes deactive. So in that case, it was a very simple on and then off again constraint change. So there's a fairly simple operation to activate that at the appropriate time. But if you had a situation where you had to activate and deactivate the constraint over and over again, you might want to do it not with a position constraint, but with an expression. If I get a new null and bring it over here, instead of using a position constraint, I'll simply go into the expression editor and equate the x location with this null's x location, and then go into a second expression for the y and then another for the z channel. It's a bit of a pain to set up because you have to do each of the channels separately. Click on validate. You can see there's an offset in the position of the end effector, and that's because its parent doesn't have a 0, 0 location. It's up in space a bit. So we could either bring that down or we could parent it to a global null. So I'll just get a new null and then use the parent feature to get that like that. And then when we hit refresh, it'll jump exactly to our null. Again, its final parent should be at the global center of 0, 0, 0 for this to really work. Now we can select our null and scale it up a bit so it's just a little bit easier to select. Now we have it working just like a position constraint. But what we can do is get a second null and have this be a switch. I'll go into info selection and call it IK switch. I'll call this one the IK target. Again, I'll select the effector and change its expression now and add a conditional function in. We'll go down to the condition and put the cursor right there, double click on that. I'll go ahead and copy that and paste it into the true section. This is what we want to happen if our condition is true. If it's false, then we want it to equal this.etran x. Of course, we could type it in instead of going into the F curves. We can do it either way. This is a self-reference, meaning to just follow nothing or follow itself if our condition statement is false. What our condition statement will be is based on that other null, the IK switch null. We'll say that if the IK switch's translation in Y is greater than or equal to 1, that way if we bring the switch up to 1, this will happen. The end effector will stick to our target null, otherwise it will do nothing. So now we'll grab this whole expression statement, copy it, and then paste it into the second expression. And we'll just change the x's, in this case, to y. And in the last channel, select that, paste over it, and change them to z's. Click OK. Now in the schematic window, you can see that the expression is relating to the IK switch null. As we bring it up over 1, our automated constraint will work. But as we bring it below 1, our automated constraint will turn off. The nice thing about this now is that we can animate the location of this switch. Using a hotkey now, I'll set a keyframe with it down, and then later on set a keyframe with it up, and then set a keyframe with it down, like that. Now I'll animate this target null moving around. As I drag the timeline now, you can see that it will not be attached, and then at a certain point, when it hits over 1, there, our end effector will grab on. And then as it gets exactly below 1, right here, then it will detach again. So this method takes a minute to set up, but then it allows us to quickly animate the position constraint on and off through the use of expressions. Now, if you animate with both inverse kinematics and forward kinematics, like I just showed, you'll just need to remember to watch out for the rotations of these joints. In versions of Softimage 3.7 or below, then when you rotate the joints, these would actually come detached from the target null, and so it wasn't very interactive. But they fixed that, and so you can just simply rotate these to basically change your preference for the IK solution. For instance, if I really torque that joint there, then the IK will honor that as I move the finger around and try to hold that position as much as possible. So you need to keep this in mind as you animate the actual joints, activating and deactivating the constraints, if you're going to use both inverse kinematics and forward kinematics together. Shoulders are one of the more difficult areas to set up properly for a full range of motion. One thing you want to watch out for is to make sure that this pivot point of the shoulder blade joint is low enough and to the side enough so that when the shoulder lifts it will curve inwards and the shoulder will move toward the head a bit. This is the Stewart character's shoulder setup that I showed in Character Kit 1. It's very simple with one single joint chain for the shoulder and then the arm was parented to it. It worked pretty good, but it lacked certain subtlety, and so you couldn't get a full range of motion out of the setup. One problem is that as the plane of the arm rotates, too much of the shoulder itself rotates with it. A better scene to show that is this scene right here. Again, I'll do the same thing. As the plane of the arm rotates, the shoulder crunches too much. What should happen is that the shoulder should mostly stay still, at least till this section right here, and this section shouldn't rotate much at all with the arm. In order to fix that, what we need to do is add a second joint to the shoulder setup. We want this joint to move with the arm as it lifts up and down and side to side, but not as it twists. So in order to do that, just get a brand new joint and then position constrain the root of this to the end effector of the shoulder, just like you could do with the arm chain. But then with the end effector, position constrain that to the second joint of the arm chain, so it will always point towards it. So if we watch that work, I'll just grab the end effector, see it will move with the arm, but when the arm twists, it does not rotate with the arm. The arm is twisting, but our shoulder joint still has the same rotation values, unlike the arm joint. But we have to do one more step to get it to not rotate at all, and that is to add an up vector constraint just for this one joint. If I turn on Show Critical Zone, you can see that an up vector constraint has been applied to the shoulder joint, and this one gets parented to the chest in some way, and you shouldn't ever move that. This is just designed to keep it from rotating as the arm moves up and down. With that new joint added, you can see that as the plane of the arm twists, that less of the shoulder moves. You can see it working a little bit better on this scene right here. As the arm twists, the shoulder doesn't really twist much at all. But as the arm moves around, of course, the points of the shoulder have to move with the arm. This allows for a pretty complete range of motion for the arm. Another problem for the shoulder area is the underarm and just underneath the underarm. All these vertices need to lift with the shoulder, but instead of lifting, they actually twist with the shoulder. Since the shoulder joint is rotating, the points in this area travel on an arc. So the end result is that they move not just up, but out as well. You can fix this problem by position constraining a new skeletal null right in the shoulder area, constraining it to the end effector of the shoulder joint, and then weighting these underarm points to that. This will make it so that when the shoulder lifts, those points will pull up because it's position constrained rather than rotate up like it is now. So here we get a new null. We position constrain it to the end effector of the shoulder joint, and then we parent it to the chest chain. The points that we weight to it are in the underarm area and a little bit around the chest. This makes much more realistic deformation underneath the arm. Bounding models really help in weighting the difficult shoulder area. Remember that bounding boxes can be ghosted and still seen in the shaded view. So here's the regular upper arm joint's bounding box, and you see it doesn't include the top of the shoulder. That's left for our new shoulder joint, and the bounding box for that looks like this. In the area that they overlap, we'll get a smooth transition in between the two joints. Bounding spheres and cylinders can't be seen in the shaded view, but if I select that underarm joint, which is actually located at the end effector of the shoulder, you can see that two bounding spheres were used to define the area underneath the armpit and also some of the area right there on the shoulder. Those combine with the bounding models from the shoulder itself, which looks like this, and the chest, which looks like that. In addition, to get the shoulder area and the chest area to weight properly and quickly, I've added a couple of skeletal nulls for the chest. These also have bounding models which define an area around the chest. These nulls aren't really necessary if you were going to use only the top joint of the spine, but they're also helpful for breathing, for simulating breathing, and I'll show that later on. Adding just these few extra controls to the shoulder setup really helps when you want to do things like raise the arm high over the head, like this. Even these demanding poses for this climbing animation worked out pretty well using these techniques for the shoulder setup. For the hips control, just like in Character Kit 1, you can make all the upper body be children of the hips, so that when you move the hips control, everything in the upper body moves with it. You could also arrange it so that the upper body was not a child of the hips at all, so that when you move the hips around, the upper body didn't move around at all and they could be completely independent of each other. This works better with cartoony characters because you can get quite a bit of squash and stretch in the body. In this case, I wanted this character to only be able to swivel his hips a little bit, independent of the upper body. Of course, you can go ahead and rotate the hips and the upper body together. But I wanted to also have the ability to rotate the hips independently, just like it was shown in Character Kit 1. So what happens is the root of the hips chain gets constrained to this control object. In Character Kit 1 I was using a box, but to distinguish it here I've just used a square shape. It doesn't really matter. It's constrained both positionally and orientationally to the control object. Then for the independent hip rotation control, we can make an orientation constraint only for the joint itself. I want the control object to hover over the geometry of the character like this. So what I'm going to do is just get that into place by using constraint position and then constraint orientation. Relax those both. Middle mouse button is relax all. Since it had two constraints, I needed to do relax all. And then I'll select the joint. Again, do constraint orientation and then pick the control object. The hips rotation object is parented to the main hips control, and then with it we can swivel the hips independently like this. The toughest part of the hips area, deformation wise, is to get this area right here as the leg moves up to deform properly. This inner thigh area of the legs here tends to collapse as you lift the leg up, and so you have to do some very careful point weighting to get that to work. Again, mostly I use bounding models with one for the hips looking like this, and then one other bounding sphere. This character shows it a little bit better. Since these vertices here rotate with the leg, they tend to intersect with the body, and also as the legs get close together and up, this area here tends to compress, leaving this sort of hole or dent area right here. Again, you can solve a lot of this through careful point weighting. The leg on this other side was fixed up more than this leg, and you can see the difference. And keep in mind that you can solve any of these deformation problems afterwards with automated shape animation, just like we showed with the legs. There are several good solutions in Softimage for dealing with long, multi-jointed chains, for instance, a tail or a spine. First we'll look at the most obvious method. If we just go and draw a new 2D or 3D chain, about in the shape of a spine. For a spine like this, you wouldn't want to use the end effector much to actually animate it, because you could only get a very limited amount of poses. You could pose the spine down like this, but what about when you wanted the spine to bend this way or that way? It could move that way, but each individual joint, of course, would not be rotating on the y-axis. It doesn't matter whether this is a 3D chain or a 2D chain. You'd have to manually rotate them into place. This is workable for a 3-jointed spine, but what if you wanted a 5-jointed spine? You'd be more likely to look for some kind of automation to help you in animating it. One way to automate it is to link the rotation of each of these joints to a controlling null. So first I'll delete that, and then draw a new chain, this time straight up and down. And then I'll get a new null. First we want to link this joint's rotation with an expression. We want its rotation in z to be linked now to the null's rotation in z. Then we're just going to copy the expression onto this next joint. Copy, and then again, copy. Now you can rotate all 3 joints at once, just like we did with the fingers earlier. To make the spine be straight up and down, instead of laying on the ground like this, we can just add 90 to the equation. Of course, all the other joints are children of the first joint, so we don't have to do that to the other joints. We could also add other axes of rotation, like the y rotation this way. Just go into the expression. We'll just make a new one, equating the y with the rotation of the null's y rotation. Unlike with the fingers, we'll want each of the joints to rotate in y with the null. So again, we'll just do an expression copy, and now they all rotate on y and on z. We could also handle joint twisting on the x-axis the same way. We'll add a third expression with the x rotation. Again, we'll just use the expression copy feature to grab the expression for the other joints. Now the whole chain will twist on x. Each of the children will inherit the parent's x rotation as well, and then rotate additionally on x, so the chain twists really fast. Just like with the fingers, this is a pretty good setup, but it doesn't really allow you to get every single possible pose. One way to improve on this would be to use a 4-jointed chain, which would give you smoother deformations anyway, and then use the expressions only on the last 3 chains. The first chain, we can just control that using another control null. I'll get a null and scale it up a little bit and place it right there. I'm going to constrain the second joint's position to the null. This way I can get a lower back control that's independent of the upper back control. You can hunch over the top part of the shoulders while the base of the spine can take any other attitude. The only thing you can't do with this setup is have the lowest joint rotate on x automatically based on the x rotations above it. So for instance, if I want this joint to rotate less than this joint here, I can't put an expression on it to equate its x rotation with the x rotation of the joint above it. An expression like that would interfere with the inverse kinematics, since the second joint is a child of the first one and must inherit all its rotations. Setting up an expression where the parent inherits the children's rotations creates a cycle and is impossible. Another way to control spines is to take a top-down approach. In the previous example, you controlled the top joint by rotating the bottom joint, and then each one up the chain. What I like to do instead is to create one joint at the top and control its position first and foremost. I make the rest of the chain to follow along with the chest or the top of the spine. You can make 1, 2, or 3 one-jointed chains as the bottom of the spine. These are one-jointed chains. They're going to be artificially linked together through constraints. And the reason we're doing that is so that we can twist the topmost node and then have the others follow in decreasing increments. First of all, I'm going to get a null, translate it up, and then scale it so I can see it clearly. I'll position it in the same place as the root of that first joint, and then constrain that root to our new null. But first we want to orient the null just like that chain root is. So there's the chain root in the schematic. I'm going to do an orientation constraint and then relax. Now I'm going to position constrain the whole top chain in both position and orientation. So now as I twist in Y, the top node will twist. Now we want to make the bottom nodes follow along with the twisting in Y. For this one jointed chain as a whole, we're rotating its chain root, and that's oriented more like the global coordinates, with Y being rotation around the global Y axis. But with these other chains, we want them to rotate on their local axis. It'll work better for the deformation that way. That's the X rotation axis, this way. So we want to equate the X-axis of these joints somehow with the Y-axis of this null. First I'll name the joint so I can more easily tell which joint it is. I'll call that third spine, spine 3. The top joint, chest joint, and this will be spine 1 and spine 2. For the control for the spine, I'll call it chest control. Now I'll put an expression on this joint so that its rotation in X will equal the chest control's rotation in Y. Now the joint moves sideways like that. The easiest way to fix that is to change the parentage of our control null. You can easily do this by getting a new null and making it the parent of our control null for the chest. Make the parent have a rotation value of 0, 90, 0, and then our child null can now have a rotation value of 0, 0, 0. You can see our secondary joint there with the expression on it has straightened out. This is the easiest way to fix that problem. Now the Y rotation for the top joint will cascade down to the second joint just like it should. Now we'll want to divide the rotation of this joint so that it doesn't twist quite as much as the top joint. So we'll just divide it in half with a /2. Now when I rotate the top null, controlling null on Y, they both rotate, but the second joint rotates half as much. Next I'll copy the expression onto the other joints, but change the division value to be greater. Copy again. Now the whole chain will twist in X, but the bottom joint will get the least rotation in X, and the top joint will get the most. Now we'll also want to control the position of these two nodes in between. We can do that by getting new nulls, and I'll scale those up a bit as well, and position them right in the intersection between the root and the end effector of the last joint. I'm going to use effect alignment to do that and get that in place. Next I'll grab that chain root in the schematic window here and constrain that in position only to the new null. I'll do the same thing for the end effector of the last chain. Position constrain it to that one. I'll just duplicate our controlling null, bring it down, get it in the right place with effect alignment, and then position constrain to that one. Last I'm going to take the end effector of the top one and position constrain it to the top null. Now the top of the chain can be controlled in Z, X, and Y, and of course the only rotation values that are passed on to the lower back is the rotation in Y, but we can also move them all independently now to create any pose that we like. The other advantage of this method is that we can position the most important part of the spine, which is the top of the spine, first, and let all the other parts follow along. The other advantage is that we can allow for lots of squash and stretch of the spine. You'll notice that spines compress and decompress quite a bit as they move around. Now here's that spine setup in the actual Stewart model. This is the low resolution character. You can see I can twist the chest on 3 axes, and when I twist it on the Y-axis, the other joints follow along in varying degrees to simulate that spine twisting. And then of course you can achieve a tight bend of the chest, or you can drag the chest over so that he'll bend over like that. And again, you have the ability to pull the spine up and down to squash and stretch. Of course, the shoulders and the head and the up vector constraints for the arms, they all get parented or joined in with that so that as you move it around, the whole upper body will move with it. And of course, you also have the ability to move the lower chains. And now switching to that high resolution model, you'd be able to see the deformation a little bit better. Like I mentioned before, these three nulls here can be used to control or simulate breathing. So I could scale all three nulls at once and get the chest to heave just a little bit, or I could translate them up or out for a little bit of chest movement. This skeletal null down here has been added to the belly area to be able to simulate the belly shaking around. Now what if your character has a really long, cartoony spine, or it has a tail? None of the setups we've shown so far will really work for those, as you'll simply have too many joints to control individually. It's just not a very practical approach. One thing you could do instead would be to attach all these joints to individual clusters on a spline. That way you could drive the animation through shape animation, and it would be really quick to grab each of the nodes. So for instance, if we just get a linear curve, and I'll put them just roughly in the areas where these joints are, and then we want to take each one of the joints and attach it onto each one of these points. Just for convenience, I'll turn on Show Point Unselected, so we can see those there. To attach a joint to these individual points, we need to make individual clusters out of each one of the vertices. This takes a minute to set up. What we do is to grab a vertex, we can go into Tag Set Cluster, or alternatively, we can go into the motion module, which we'll need to be in anyway, and use Shape Set Cluster. We can leave it at the default, and then tag the next point, set a new key, and so on. Once I have all the tagged point sets, I'll go into the cluster list and change to the first cluster. Now that I have that selected, I can grab the root of the whole chain, but instead of doing constraint position, we have to do a object to cluster constraint. Now I'll select anywhere on the spline, and the whole chain will jump to it. Then I need to reselect the spline and switch to the next cluster, and repeat, this time with the joint. Again, I'll switch to the next cluster and constrain this one to it. Object to cluster. And we'll do that down the line. Now we'll be able to move these points, and the chain will follow along. This isn't worlds ahead of what we were doing before, but it does allow us to get the pose really fast. What we would do to animate it then is to use shape animation. Shape animation might be useful because of the blending you can get in between poses. For chains like this, it's going to be easier just to use shape animation, since it's just one pose for the whole chain instead of lots of individual F-curves to animate. So we can go into Save Key, Object, Shape, and go to a different frame and make a new pose, and Save Key again. Now the disadvantage of this method is that if we wanted to rotate the first couple of joints in X, then all of them will follow along, the whole chain. If this were the base of the tail, we would want this to rotate more in X, and the next joint to rotate less and less and less, until the end maybe it didn't rotate at all. But this setup doesn't really allow for that kind of motion. Instead, you could create a series of single jointed chains to create what you might call an artificial chain, and then attach them afterwards to a linear spline like before. Again, I'll make clusters on each point like before, and then constrain the individual single jointed chains to them using object to cluster. This time, instead of the joint, we'll attach each root to the cluster, then of course the end effector to the next cluster. This will work a bit differently from the single multi-jointed chain because it will pull apart, which may or may not be the effect that you're after. But the advantage of this again is that you can have the one joint rotate in X and the others follow to decreasing degrees. If this were a neck for a dinosaur or something, I would want to be able to rotate the first joint of the neck, the one closest to the head up here, and then rotate that one or twist it in X and have the others follow. So I'm going to change the name of this one to head and then have this one follow its X rotation, and then I'll divide that by 2. So that works okay, and then I'll copy that expression onto this joint and divide it by 3 or something like that. Do it again. divided by 4. So that's working pretty well. First one twists a lot, and it successively lasts down the line. This is a character I made for King Television in Seattle for some television commercials they had made. The design itself was done by Disney Studios many years ago and was brought back for this series of promotional TV commercials. His head is like a microphone, so they've called him King Mike. His cape was done the same way that neck was. This is the spline that all the joints are attached to. It had this extra point sticking out here just so it could be easily selected. You can move the points around and affect the shape of the cape as a whole because the joints were attached to it. This was the system of joints that was used to form the skeleton for the edges and 2 ridges down the back to be able to deform the shape and have some flexibility too. You can animate that spline with shape animation, but the spline itself was also linked to the body parts. So all of the upper body, for instance, could be rotated or scaled, and the cape would follow along too. In addition, I also had a group of nulls on the floor to which the spline itself was constrained. This made sure that these points on the cape were locked down and wouldn't go underneath the floor when the body moved. So I could use a combination of shape animation and skeletal animation to drive the motions of the character. So here when I pull the body forward, for instance, the back of the cape stays where it is, and I can animate that separately if that's convenient. Or I could disable the constraints if it wasn't convenient. So where the chains are attached to the spline using object cluster constraints, bottom of the spline and the shoulder areas are attached using cluster to object constraints, so going the other way around. And so each one of these is attached. So when I scroll the timeline, you can see how it works. The top of the spline is attached to the shoulders, and so that made it move with the body, whereas the bottom of the spline is attached to the floor, so it stays statically attached. Also notice that just like the tail setup, it's one continuous spline all the way through the entire cape. This just made it easier to shape animate since it was just one object. So that was using single jointed chains that were attached with cluster constraints to the clusters on a spline, and then some of those clusters were attached onto nulls to keep them still during animation. But you can also use another level, which is to deform this curve onto another curve. First, what you need to do is draw the spline straight up in the global center, and we'll turn on grid lock in Y and Z, draw a linear curve, just like before. And then I'll just go ahead, make the clusters, and then attach the joints to the clusters. Again, each cluster has 2 things attached to it, the end effector, the last joint, and then the root of the next joint. So now I have this linear spline, which is exactly at the global center and is pointing upwards. And we're ready to make our new spline to deform it too. I'm going to turn off the grid lock, and then draw a new spline. It can have any number of points and be any format, but it seems to work good with cardinal. But when I have that all ready, I'll just go to Deformation by Curve, Node, Create. Then I'll pick the new spline. If we draw it right at the global center straight upwards, it'll form right to the spline but then be too small. So what we'll need to do is scale it on Y, this is the linear spline that is, until the joints exactly align with the last joint. So for instance, if I zoom in here, we want to get it so that the end effector of the one is matching the position of the root of the last one. So right there. And this will often be a scale of about 1. Now what we can do is, using these points, slide the points around. Softimage's deformation tools will keep the one spline on the other, and we can use the controlling spline now in an interesting new way. Since it can glide across each of the joints, we can make really any shape possible. The chains also rotate very subtly on their x-axis to follow the shape of the guiding spline. So you can watch this joint right here. As it goes up, it twists slightly. Since each of these is a single joint chain, we can do the same thing as before, driving the X rotation near the head so that it will cascade down the first part of the neck, so you can do a head shake or a head roll in X. The last method I'll show uses the frame offset feature. These joints here will follow the rotation of the first joint, but lagging behind a certain amount of frames so we can get an easy whip-like motion of a tail. Again, we need to use single joint chains artificially linked together. We can do that by position constraining each of these roots to the last end effector. Then we're going to note the name of this first joint, which is joint 94.1. Then we need to get a new null. The null we'll use as a slider to change the offset, the number of frames that the joints are offset from each other. So we'll grab this second joint here and go into Expressions Edit. Then we want to relate its rotation in Z to that first joint, joint 94.1, its rotation in Z. But then we want to put this frame offset in there. So for the element, we'll include just what we had. Now this FC minus 30, this will tell us how many frames to offset. We need to take those off, and we could just use a straight number for each of these, but if we use that null as a slider, then we'll be able to change the rate at which the joints lag behind the first joint. So we'll go into Scene Elements here and pick the null, and then for its function curve we'll do its translation and Y. We could choose anything. And then we want to multiply that by 1.5, or some number, which we can increase for each of the joints down the line. It won't lag behind it yet because we haven't set any keyframes. So if we do that, nothing's going to happen yet. So let's do that. First we'll go to frame 0 and set a rotation keyframe, and then go forward a few frames and save one with it up like that. We'll go forward a few more frames and save another one. So as we drag that up, you can see that the angle of that second joint will change. So you can see it lagging behind right now about 1.5 frames. Next we're going to copy the expression down the line here for each of these joints. We'll use expressions copy. Then I'll just go back to this joint here and start editing the number by which it's multiplied. Now when we play it, we can see the whole chain will move in the whipping tail motion. As you drag this up and down, you can increase or We showed this foot setup in Character Kit 1 where the foot could pivot off the ball of the foot or the heel of the foot. On each of these nulls here there's an expression. If the null was above 0, then this null would rotate with it, and if the null was below 0, this null would rotate with it. So that's how these could pivot off each other. The foot would move with this controlling object here, and then also you have the added benefit of being able to twist. In this section we'll talk about enveloping concepts we haven't covered yet. Bounding models offer a way to control vertex weighting over regions rather than point by point. Bounding models themselves don't show up unless you have show controls on. They normally look solid like this in shaded mode, but if you ghost them, then you can see through to the surface. We've already shown how to place a lot of the bounding models. But one thing to note is that all the time I've used inclusive limit bounding models, which is the least intrusive of all the bounding model formats. Inclusive limit bounding models do nothing more than limit that joint's influence to a certain area. They don't force the weighting to change in any other way. They only limit the distance across the model that joint can influence. If these were inclusive bounding models instead of inclusive limit, every vertex that falls within the zone would be assigned 100% to that given joint. The only fall off would be exactly where the bounding models overlap. This way you could consider more intrusive because it takes over the vertex weighting in a bigger way. Exclusive bounding models do a similar thing. Wherever one is defined, those vertices can't be assigned to the given joint. Bounding models can't be converted from one type to another. You have to define its type when you first create it. Keep in mind though that you can assign bounding models over and over again without coming out of the mode. For instance, if we just go in to inclusive limit bounding models, we could left click to add a bounding box, and keeping in the mode we would just switch to the next one and click again, switch to the next one, click again, and so on. Of course we would need to edit those points a little bit, but doing it this way saves some time. A typical workflow with bounding models would be to assign them to each of the joint or skeletal objects, move the points around, and then use reassign automatically to get them to take effect. Once you've done that, you can create an animation showing different poses and some motions in between poses to see how your envelope assignment is working. Each time you find an error and make a change, use reassign automatically again and scroll a timeline again to see the results. One of the most important byproducts of using bounding models is that you can quickly regain all your weighting work as soon as you find any error or mistake in some part of the skeletal setup. For instance, if one of the fingers is parented to the root of the hand instead of the end effector of the hand, you would need to cut that, parent it to the correct place, and that would destroy some of the weighting in the hand area. With bounding models, you can quickly reload all the weighting work you've done without having to start completely from scratch. Only when you feel like you've gone as far as you can with the bounding models should you start to do point-by-point weighting changes using modify weights or reassign manually. Of course, bounding models can't solve every problem. In areas where there are lots of parts close together, like with the fingers, we'll need to use modify weights quite a bit to get those points to work out, like we showed in the hand section. Keep in mind that also, when you're in the modify weights dialog box, you can certainly scroll the timeline to see how your change is going to be affecting the model throughout the animation as well. It's best if you don't have to, but remember that you can remove any part of the envelope, not just the whole envelope, from the skeletal system. As well, you could remove any part of the skeleton from the envelope, make changes, and put it back on. With the envelope, you just need to grab the part and use cut. This removes that part and all of its children from the envelope. You can reattach it to the envelope by simply parenting it back into the hierarchy, and then it would bring up the assignment box, but this time it would be only for the part that you cut off. This is much safer than reassigning the weights for the entire envelope, because any custom work we've done after bounding models won't be erased by this action. It is using the default weighting, so we would have to go back in and reassign those points. Another way to save and then restore envelope weighting is to use Softimage's new skin, weight copy, and weight paste features. To make sure it's working, let's just select a few vertices here and then assign them to something different. We'll use modify weights, then scroll down to something like the chest joint. We can assign them 90% to the chest joint, and of course it won't work for the envelope, but it'll let us make sure that we've gotten exactly the same weights back after the operation. So what we can do is go into skin, weight copy, then we'll name it something like arm left. Next it'll ask us to pick a skeleton element. Normally we could select just the arm, but since we've attached some of these points to the chest, we'll need to select the root of all the skeleton elements in the character. All the skeletal chains have been attached to a single null, and so we'll just click on that one right here. Next we'll do a reassign automatically just to that one part of the envelope. So that's reassigned. Now when we drag that, we can see that the fingers have become screwed up since we've gone back to the initial bounding model state, and then the points that we assigned to the arm to the chest are back the way they should be. So what we'll do now is go back to the default pose and select that part of the envelope again, and we can recall those weights using skin, weight paste. We'll browse for that file name. It'll ask us to pick that same skeleton element. First it'll make sure that all the skeleton element names are the same, and then it'll interpolate the weights from the save file onto our envelope. This normally takes a few minutes, and if I have the whole thing selected rather than just the arm, it takes a very long time. Once it's done, we can grab the end effector and see if our weights have returned. And sure enough, we have just the same points misassigned, and the fingers have been fixed the way they were before. Again, the only drawback to this feature is that it's very slow, but otherwise it's extremely valuable. Earlier on in the tapes, I mentioned how you can transfer vertex weights from a low resolution model to a high resolution one of similar proportions. This is the feature you would use. It not only interpolates weights between vertices that are already there, but if we were to subdivide this, we could use the same feature to transfer weights from one to the other. When you begin the animation stage, you're going to want to pose the character as fast as possible, and you're going to want to play the animation back as fast as possible too. Just a single character of this complexity here makes the scene pretty slow. If I hit the play button, I see I'm getting a frame rate of about 0.65 with the envelope fully active. There's a couple ways you can speed that up. In Character Kit 1 I showed how you can select the whole character and go into Flex Env in the dope sheet and just deactivate the envelope. Now when I play the scene, the envelope won't update, and I'll get a faster frame rate somewhere around 1.2. I'll just toggle that back on. Another way to speed it up is just to hide the geometry of the character. So if we hide that part, and then the teeth here, and we hit play, we'll get a much better frame rate than before. So that speeds things up a bit, and the scene will go faster. But the fact is, Softimage is still computing the envelope, even though it's hidden. A relatively new feature in Softimage is the ability to make it so that it's not computed at all. Anything that's hidden will not be computed if we just use update visible instead of update all. Now the scene will play back quite a bit faster, running at about 5 frames per second. And of course, if we go to wireframe mode, then we'll get an even faster playback. Also, since there are some NURBS elements in this scene, if I go into setup, change the surface precision to 1, I'll get a faster playback as well. But better than just animating the wireframe skeleton, and almost as fast, is to make a low-res version of your character. Now this character is already polygons, so all we need to do is select a part of it and detach those polygons. If it's NURBS, we could convert it to polygons using a step of 1 to 1. To do this, we go back to a frame 0, and then since this section of the shirt and the arm will include both objects, we'll merge those two together. Now for the upper arm, we'd want to just select the polygons in this area. What you're doing is selecting the area that will be affected by this one joint. So now we'll just use polygon, polygon detach, and then click off hierarchy of polygons. This creates a new object, but if we look at the edge flags, we will need to clean it up. We'll go into Effect, Cleanup, and turn on Merge Unconnected and Merge Near Points. And then it's ready to be used. To use it, we'll grab the right joint object. Then we'll simply make this object a child of the upper arm. Once we've made those objects all over the body and then parented them to the right joint, we can just hide the high-resolution envelope. Now we'll have our really fast playback, but with a better visual representation to look at than just the skeletons. So you don't have to have a separate character model or a separate scene to have the low-res version. The low-res version can simply be attached to the same skeleton that the high-res version is on. These are simply children of the same joints that are deforming the high-res model, which is now hidden. You can switch easily between the versions using name selections. First, what you would do is multi-select all of the low-res parts. Once you have them all selected, go into Select Set Name Selection, and you could name it something like low-res parts. Now you can quickly hide these parts or show them using the name selection. The quickest way to do this is to hit Enter and then double-click on the name. From here you just click on Hide or Unhide. An even faster way is to multi-select all the low-res parts and all the high-res parts, so that when one is hidden and one is showing, you can toggle. Just by changing Hide Toggle, we can switch quickly between the low-res and the high-res versions. If you have a name selection like that, you can just hit Enter, click on Res Switch. This time we won't want to do hide and unhide them all. Instead we'll select node, and then toggle their hidden status. Of course, it isn't as useful as seeing the high-res model, but it's a lot more useful than just seeing the skeletal wireframe. But even with these pretty good frame rates, it's still going to be hard to know exactly what the animation is going to look like in full motion. So you probably know about fast playback. Go in the layout, you can turn on fast playback. Then when you hit play, it'll store a screen image for each frame for the animation. Then when you hit play again, it'll play it in real time. But unfortunately this only works in a wireframe mode. Another thing you can do is go into play control. Here if you change the frame step to 0 from 1, then it'll play back in real time and just skip all the frames that it can't play. So now you can start to get an idea of what it's going to look like. Even if it's a little jumpy, at least we're seeing it at the intended speed. And especially if we go into wireframe mode, then we can get a really good idea really fast without having to use fast playback. And we're getting about 7 frames per second anyway, so we're not skipping a whole lot of frames. To get a more accurate playback where you're seeing every single frame, the only way to do it is to render a flipbook. Of course, the fastest renderer is the OpenGL hardware renderer. Once it starts up, it goes really quite fast, especially with only the low-res parts showing. If you want to render out a fast wireframe preview, don't use the wireframe setting in the rendering. This is a slow vector-based format with large file sizes. Instead, use the OpenGL renderer, but first turn on fast playback. Then when you do your render, it'll do it in wireframe. So here's a rendered flipbook. It took about 1.5 minutes to render that 130 frames, which is pretty good. The next thing you want to do is make sure that all the controls that you'll be manipulating for animation are easily selectable. A lot of these controls are made purposefully oversized to overshoot the boundaries of the geometry here, and that's just so I can go in and select it faster, like that. So the nulls for the shoulder and the hands are scaled up quite a bit, so they'll be easy to select and easy to see. The next thing you can do is select all the low-res parts and then make them unselectable. That's of course using select, selectability, toggle selection. That'll make sure when I'm going to select something like the wrist joint that's embedded inside the arm here, I won't select the geometry by mistake. Make sure you get acquainted with the transformation setup feature in Info Transformation Setup. With this you can determine exactly the transformation mode that engages as soon as you select this object. So for objects like this, you'd want it to translate in all three axes in drag mode, whereas maybe for the chest, you'd want it to rotate every time in any of these or all three axes. This can speed up the workflow immensely because whenever you select an object, you're ready to go and you don't have to go over and select a transformation mode. It already knows what you want to be using. So as soon as I grab the head, it knows that I want to rotate it. As soon as I grab the hips, it knows that most of the time I'm going to want to rotate it in Y, switches to Y mode. As soon as I grab the boot, it knows I want to rotate that in X. As soon as you preset those, you can find you can work a lot faster. The default updating behavior for Softimage goes like this. You can of course move a keyframed object to another location, but then as soon as you grab another object and move that, the first one will jump back to its keyframe position. This isn't very conducive to throwing together a pose for the character, because each time you'll have to set a keyframe. So rather than having to worry about setting a keyframe every single time you want to move an object, you can set this environment variable for Softimage, set si no interactive f-curve update equals 1. I mentioned this in Character Kit 1, but I didn't really show it and explain the difference. When that's activated, the update behavior is much nicer. You can move objects that are keyframed, and the first object you move won't jump back to its position. So this way you can throw together a pose very quickly. Once you have a pose that you want to keep, you can keyframe them all individually, or you can use, again, set name selection. I have a name selection called translation keys. This is a collection of all the control objects that have to be keyed in translation for the pose to stick. I can select all of those and then keyframe them all together. Then I can select all the rotation keys and keyframe those all together. If you haven't already, go ahead and make hotkeys for saving explicit translation and saving rotation at the very least. You find that you use these so very often that it's just useful to have them right there on the keyboard. Also, in the animation preferences, make sure you know how to use no confirmation required. With this activated, if you happen to be on a frame where there's a keyframe of that type, when you change things, then that keyframe automatically gets saved. If I'm on another frame and I make a change, that doesn't get saved. Same thing goes with translation. If I'm on a frame without a keyframe, it has no effect. But if I'm on this frame, then just by moving it, I've changed the animation. And it's the same as if I had saved a keyframe with save key. That feature comes in handy especially when you take a pose-to-pose approach. You can think of the animation as a series of poses. Concentrate on getting a dynamic pose, and then move to a new frame and make the next pose. It doesn't make sense early on to get caught up in things like interpolation between the frames. To rough out this animation, I just created a series of poses, and with the play control set at 0, we can zip through those in real time and get kind of an idea of what the animation will look like. In the dope sheet, we can use Shift middle mouse button to alter the overall timing of our character, with either nothing selected and changing the scene, or the whole character selected. We can shift around keys very quickly in the dope sheet, and then replay the animation. A lot of people find it useful also to set the initial default F-curve interpolation to constant. This way the F-curves look stair-stepped like this. Keyframes just move from one position to the next with no in-between state. And that way we can focus on the poses and not have to worry about interpolation yet. To change poses, we can turn on the keyframe option, and then when we hit play, we'll just jump to the next keyframe position, and we can very quickly alter our poses. We could continue on like this, creating more and more key poses. Then once the timing and the poses look good, we could switch the interpolation of all the objects to a smooth one and refine the animation further. To do that, we could just multi-select all the control objects in the schematic window. Then using F-curve select object all, we could then select all the curves and change them to something like plateau or spline. At this point, you want to begin to use function curves and edit the function curves, since they give you the greatest level of control over the motion. Make sure you're familiar with the update options It used to be we only had no automatic update, but now we can choose to update the scene when we release the mouse button or continuously as we edit the function curve. So with continuous set, as I drag the point on the function curve, it updates as we go. At least the control object does, and when I hit refresh or scroll a timeline, then the model will match the controls. But even having this, especially with rotations, helps you to see which axis is which. Studying the function curves will let us solve problems in the animation. When you have a region of the animation you're going over again and again, remember that if you hit the middle mouse button on the play button, it'll start playing from the current frame and not go all the way back to the start. As you get closer to having motion that you like, you'll eventually need to switch in the high-resolution version. Then you can study things like facial expressions, deformations like breathing, and interpenetrations like with the hand. You'll find that you can be much more critical of the animation looking at the high-res version, and the closer you get to your final output, the more you'll see things to fix. Not only are their fingers interpenetrating on the left hand here, but they're opening kind of fast, and it looks kind of strange, so that's something I need to fix. So these are the things that should help your animation go quickly and smoothly. So far we've looked at things that'll help you in a production environment. Number one, you want flexibility in your character. You want to be able to get the performance out of them that you need, and that's mostly what the character setup section is all about. Controls that'll help you get the best performance out of the character. And so far in the animation section we've looked at speed. You want to be able to do those things quickly in production. Next we'll take a look at some animation principles and how to implement them in Softimage so you can get strong character performances. First we'll look at the principle of squash and stretch as it relates to characters. With a simple sphere we can not only scale it uniformly, but if we switch to volume mode, we can scale it so that it scales up in one direction and down in the other. This way it always keeps its volume no matter what the scaling is. But with characters it's hard to use that particular feature because most of the character parts are interrelated and attached to skeletal systems. If you have a discrete disconnected part like this head here, you could apply that volume scaling to it, and you could get that to work a little bit. But it would be more difficult to utilize on something like a hand, a complex skeletal system, where scaling one object doesn't really relate to the scaling the next. Alternatively, you could get squash and stretch as well by applying a branch lattice to a discrete object like this head portion. Then just by moving the points of the lattice, you could deform and squash the head and simulate a cartoony, kind of wacky squash and stretch. Another way is like the back setup we did, where the joints of the spine are part of individual chains. This way, as the character reaches up, you can also stretch the backbone out a little bit to match, and also using the nulls to stretch the other ones up as well. Next is the principle of anticipation. This is when the character recoils before doing something else. In general, the greater the power of the thing he's trying to do, the more intense the recoil will have to be. In this case, the character is throwing his body one direction in preparation for an exuberant shout like that. Look at everything that's going on to make a successful recoil. He doesn't just go from this position here to that position there. In order to get there, he lifts his shoulder, then he puts his arm back, he arches his back, and then he twists his back. His other hand lifts up a little bit, and he stays in that position for a few keyframes before punching his arm up like that. As he comes out of the recoil, notice the other arm gets thrown back as well. So the greater the recoil, the faster the action afterwards should happen. Compare that with how King Mike's arms recoil. As he goes to stick his hands out, he brings his arms up. He spends several frames preparing for the bringing his arms out, and then starting here, within 2 to 3 frames, he pops his arms out. It's not as big of a motion as the other one, and so it requires less of a recoil. Whenever a character has to exert himself to do something like getting over this concrete wall there, then that part's the recoil of the anticipation, and it needs to go a little bit slower. Follow-through is what happens after the character hits the pose. After King Mike sticks his hands out and reaches the pose, you see his head keeps on moving a little bit. The end of the action isn't like hitting a brick wall. After exerting a little bit of force, his body will continue in motion a little bit. This is related to the idea of the hold and the moving hold. Seldom in CG do you want a pose to be perfectly still. So if you watch some of the objects moving after the pose is struck, you can see what I mean. His weight relaxes a little bit and his pelvis goes down. His hands don't stick in the exact same position, they move a little bit, and his head rotates into position a little bit. Another example of follow-through is when Vigilant hits the ground here. His chest and his arms react to the impact by moving down and then moving up. Here's the F-curve for the chest motion. You can see there's a quick dip and then a bit of a return to its normal state. A similar thing happens in its rotation F-curves. Then of course the arms are moving down as well. A related concept to follow through is the idea of secondary action. This is areas like the belly and hair, things that don't move in and of themselves,